All right. So we're moving into a section 19, and we're going to dig in more with aldehydes and ketones. Aldehydes and ketones. I want to give you guys a perspective of how these are abbreviated. I maybe have shown this before. Aldehydes are often abbreviated with that CHO, and ketones often abbreviated with a CO or even a CO in parentheses to designate that that oxygen only belongs to that ketone. Carbon. All right. I think what I want to start here is dissect a little bit about the functional groups that we're going to be looking at in our. You guys can see that this unit 4, is all about carbonyls, aldehydes, ketones, carboxylic acids, and what are called the carboxylic acid derivatives. So I want to dissect a little bit about their reactivity, their nomenclature, all of that good stuff. And I think we'll do section 19. You guys will have your homework on that, and then we'll come back in with section 20. Quite honestly, section 20 and 21, you guys might have noticed this. The pre-reading quiz is just one quiz. Section 20 and 21, they bleed together. It's really hard for me to differentiate them. You may see some textbooks that differentiate them. I separate them so you can see the distinction, but they do bleed a lot. When looking at a carbonyl, I'm just going to give this generic baseline here. So what is R? Could be a hydrogen, could be a carbon chain, could be an oxygen chain, could be a chlorine, a nitrogen. What is R prime? Same thing, doesn't matter. But what I'm showing you is just the snippet of a carbonyl. The carbonyl carbon and the carbonyl oxygen are going to be incredibly important reactive sites for us in this unit and the next. We've already looked at the reactive site of the carbonyl carbon. We've done acyl addition quite a bit. So the carbonyl carbon is what type of reagent? Is it an electrophile or a nucleophile? The carbonyl carbon. What does that mean, Sam, that it's an electrophile?
It usually takes electrons.
Good. So if we wanted to indicate something will take electrons, what charge is best to represent it with? A positive charge, exactly. So I like to show electrophile positive, right? Because this is something that will take electrons. You could even go right next to that carbonyl carbon and say delta plus, delta positive. So Caesar, what does that make the carbonyl oxygen? That's our nucleophile, best represented with what? A negative charge. And again, partial negative next to that. Do you think that the carbonyl oxygen is really a good nucleophile? Do you think that it takes its electrons and gives them away readily? Why not? Why would it not be good at giving away its electrons?
It's
It's got an octet, but I'll tell you something. If it shares its electrons to make a new bond, probably still has an octet. It's one of the most electronegative atoms, which means it's, oh, I see what you mean. It's not as willing to share its electrons, okay?
So I was going to say, right there, it's pretty stable.
What do you mean by stable? We already said it has an octet, but even if it makes a new bond, it still has an octet.
Right, but with the molecule it's on, like it's not looking to get more right now because it has a partial positive, partial negative charge within the.
Or maybe instead of even drawing our attention to the partial positive, partial negative, we could say it's neutral. The oxygen atom is neutral. Think about other oxygen atoms that are neutral. The oxygen of water, the oxygen of alcohols, the oxygen of ethers. We've covered all of those in the last section. And how good of nucleophiles are all of those? Pretty bad nucleophiles. No, weak nucleophiles. They're better than some, but they're weak nucleophiles because in order for them to be a nucleophile, they have to take on a positive charge, and an electronegative atom is not looking to take on a positive charge. So, yes, these are weak nucleophiles, but maybe a better way to phrase this is that these are weak bases. What I mean by that is these oxygens are not looking to go form bonds to carbon, but they could probably be convinced to take on a proton. They can become protonated, but it's unlikely that they will do a substitution reaction, right? So we're going to say that they're weakly basic. And again, all bases are nucleophiles, but not all nucleophiles are bases. That's what we're looking at here. Okay, there's some more anatomy of the carbonyl that I want to talk about because Unit 4 and Unit 5 are going to talk about this. The carbonyl carbon is the region of interest in Unit 4. When we get into more of Unit 5, we're actually going to look at these next two positions away from the carbonyl. When I teach OChem 1, the term alpha carbon comes up a lot. And I like to tell my students that's your point of interest. That's where your functional group is, maybe. That's where you want to look for reactivity. But when it comes to carbonyls, the carbonyl carbon is a point of interest, but it's not referred to as an alpha carbon. The carbon off of the carbonyl is our alpha carbon. This is just how we'll refer to it. And that gives us the chance to say alpha halogenation, alpha whatever. And the position after alpha, beta. And if we actually just take a second to think about reactivity of these places, are those carbons electrophiles or nucleophiles? Should we suspect any sort of reactivity from those carbons? What kind of reactivity do you think they would do? Especially as they are right now. Can they go through substitution? Can they go through elimination? Not easily. Can they go through addition? Actually, that's the one that's like absolutely no, they can't. There's no pi bond to consume or a ring to consume, not at the alpha and beta carbons. Maybe they can go through substitution. You'd have to get rid of that halogen or the hydrogen. Maybe they could go through elimination, but especially as it is, it'd have to be dehydrogenation, and chemists aren't very good at doing dehydrogenation. What about bases? Are those alpha carbons or beta carbons bases at all? Like a Bronsted-Lowry base. they'd have to have a lone pair that they could use to accept a proton, and they're satisfied as is. Are they acidic? Why not?
Don't want to give away.
Did you ask them? You asked them if they wanted to give away their stuff, and they said no? Yeah. Because carbons are generally non-acidic. If you look at this pKa table that's on our front page, you can see the alkane carbon, sp3 carbons. Their pKa ranges from 50 to 60. That is incredibly basic. The worst kind of acid you can have. Look at hydrogen. Molecular hydrogen has a pKa at 36. Molecular hydrogen is more acidic than sp3 hybridized carbons. But then look at carbonyls. The alpha carbon has a pKa ranging from the 15 to 25 region. So why? Why is the alpha carbon so acidic? Beta carbon, non-acidic, pKa greater than 50. Alpha carbon, weak acid, pKa between 15 to 25. What do you think's up with that?
Resonance.
Exactly. You can kind of see it, right? When the alpha carbon is deprotonated, when the alpha carbon takes on a lone pair, you create a system for resonance. You create a conjugated system. The alpha carbon has the charge, carbonyl carbon, and the oxygen have the pi bond. So we're going to spend a lot more time in Unit 5 looking at this stuff. And we're going to spend most of our time here in Unit 4 looking at this stuff. But I'll tell you what, the carbonyl makes up the rest of our class. Sound good? Great. Let's talk about the electrophilicity of our carbonyls. It's a fun word. Isn't there a book with a girl named Felicity? She's an American Girl doll?
She's also a character on the Arrow.
Oh, yeah, my mom used to watch The Arrow. Felicity Jones? Is that the American Girl doll, or is that from The Arrow?
Felicity Smoke is from the Arrow.
Felicity Smoke.
Yeah.
Felicity Jones. I think that's the person. Do they have last names?
Felicity Jones is an actress,
Oh.
and an English actress.
Oh, it's a person. Okay, that's
Yeah.
Rogue One.
interesting. All right. So, I'm gonna give us the whole list, and we're gonna dive into it for this section. We might review it again when we get into the next section. And I think we have already seen this a bit. We're gonna expand it a little bit more now. So on the highly reactive end, highly electrophilic, we have our acid chloride. Why is the acid chloride so highly electrophilic? Well, it's already got a partial positive from being in the carbonyl. And it has this inductive effect from the chlorine. So it's got this induction from chlorine pulling away from it. Next to this is the acid anhydride. Remember that it's called an anhydride because it is acid minus water. So really, they maybe should have called it the diacid anhydride, right? When you take two acids, merge them and remove a molecule of water, you get the acid anhydride. Now, this also has some inductive character away from the carbonyl. The strange thing is which carbonyl gets inductive character pulled away from it, because that would kind of imply that the inductive character is getting pushed towards the other carbonyl. And we'll talk more about that in the next section when we get to anhydrides. Our next most reactive is the aldehyde.
Wait, sorry, can you explain that again? So induction from both carbonyls?
No, it's a little confusing, and we'll come back to it when we talk more about aldehydes. But each carbonyl is essentially experiencing induction away from it due to the oxygen pulling on it, but also the oxygen can be involved in resonance with the other carbonyl. We'll compare it to the esters and the acids in a little bit too. The next most reactive is our aldehyde. This is where induction really stops being so much of an issue. If anything, we might think of reverse induction, where the hydrogen is giving its electrons back to the carbonyl. After the aldehyde is our ketone. And I'm going to represent this with R and R prime, just to say that the ketone can have different groups on either side. They can be the same R group, they can be different groups. This is where I'm going to say that induction actually pushes towards the carbonyl. What does that do to the electrophilic character of the carbonyl? It weakens it, makes it less reactive, less electrophilic. Remember that induction is a push and pull. It's all about, do you have an atom that pulls strongly, or do you have an atom that can have its electrons pulled? Or a group of atoms. After the ketone is our carboxylic acid. So I want you guys to compare for now where the carboxylic acid is in the list next to the anhydride. And I want you to think about the difference between them. Why is the carbonyl of the anhydride so reactive? Even though it's attached to an oxygen. And the carbonyl of the acid is not as reactive, even though it's just attached to an oxygen. Are they not attached in the same way? Well, technically, no. They're not attached in the same way. The oxygen of the carboxylic acid can actually donate electron density to the carbonyl carbon. Sam, your question is? Why can't that? It can, but it can also donate electron density to the other carbonyl. So, we have to imagine both carbonyls are individuals. And at any given point in time, the oxygen will share electrons with one or the other, but its ability to share with both is not as strong as this oxygen. And I said here that this carbonyl was actually reactive because of induction. Oxygen is electronegative. It pulls electrons away. Is that oxygen not electronegative? Is it not pulling electrons away? It is, but it's counteracted by the resonance. So the oxygen can share electrons with the carbonyl carbon, weakens the partial positive on the carbon. In fact, it strengthens the partial negative on the oxygen. This oxygen can also participate in resonance, but it does so to both directions, which means that its inductive effect is a little bit more apparent because its resonance effect is much weaker. Yeah? Trying to think of an analogy here, like, is it easier to pull a guy up off the ledge of a cliff with your one arm, or if you had to pull two people up off a cliff? Which one is going to do better at pulling the people up the cliff? You're splitting your ability to do something, splitting your ability to make the carbon less electrophilic, by being in resonance with two carbonyls. Here, that resonance is much more effective. What do you think the natural progression would be after the acid? I think we might have even seen this. Well, let's keep the same amount of resonance and let's look at more induction. What functional group is this? That's our ester. The ester is more stable or less stable than the acid? By more stable, I mean less electronegative or more less electrophilic or more electrophilic? It's less electrophilic. The oxygen can share electrons with the carbonyl, weakens the partial positive on that carbon, but the carbon group is now pushing induction in towards the carbonyl. So it has an even smaller partial positive than the acid because it gets the same amount of resonance plus it gets that induction. After this, we have our amides. Now, what I'm going to put here is R2 prime, but there is another way that we could say this. We could actually say N R prime R double prime. What we're trying to highlight is that the nitrogen of an amide can have up to two distinct groups attached to it. It could be NH2, in which case R prime equals R double prime. It could be NHCH3, or it could be NCH3 and CH2CH3. There's a whole world of possibilities there. Why is it that the amide is more stable, less electrophilic than the ester? Why is it the positive charge on the carbon is less willing to accept electrons from something else? Does it have resonance? In the same way that the oxygens can donate electrons, nitrogen can donate. Actually, I'm going to clarify. It's not in the same way. Nitrogen does it better. Nitrogen shares its electrons more fully. Why? Exactly. Less electronegative. I don't know if this makes sense. Less electronegative resonance. No, maybe I can say less electronegative plus resonance. Actually, I think it would have gone better flipped. Resonance plus it's a less electronegative atom. So if anything, the sharing of the electrons is just stronger. Oh, bummer. I was this close to getting it all on the board. If facility services didn't want to mark it so much, I would have had it. The last group that we will cover this in this unit is the nitrile, the cyanum. And I'm not sure that you guys are all familiar with it being called a nitrile, so I'm just going to clarify that. Why is it that the nitrile is so much less reactive than everything else? You know, triple bonds are strong and weak. Cumulative, breaking all three bonds requires a lot of energy, but each bond individually is not necessarily challenging. The first pi bond might be the easiest. The second one might take more energy. The sigma takes the most. Well, first of all, it's a carbon bonded to a nitrogen. But does it have resonance? No, it really doesn't. That nitrogen can't donate into it. Does it have induction? If anything, the carbon has induction away from it towards the nitrogen. The nitrogen could be a nucleophile, but it's not a very good one here. Actually, because of its sp character. I'll be honest, I don't know that I have the best way to explain to you why the nitrile is the least reactive. But if you want to look at it as the odd man out, it's the only sp hybridized carbon. So maybe something is going on with its bonding character. Something's going on with its orbitals that makes it more challenging for that carbon to accept electrons. You know, there's something to be said about the symmetry of the orbitals that need to be attacked, and the trigonal planar carbon might have just a better setup for that. So this is our least reactive. I'm going to put that blue to match the other end. Least electronegative. Does that mean that we will not be able to do reactions with nitriles, that we won't be able to take advantage of that partial positive? No, it just means that we will need the harshest conditions. Strong acid, strong base, heat, long reaction times. But we can take advantage of them. All right. While we've got these all up, we're also going to be talking about nomenclature in this unit. So I think we will run out the clock today covering nomenclature, and tomorrow we'll narrow in a little bit more on reactions with aldehydes and ketones. This might be a little bit challenging. I don't want you guys to make your notes too messy, but one thing I do want to clarify is aldehydes and ketones are not considered carboxylic acid derivatives, but all of the other groups are. except for the carboxylic acid. And when we get into section 20 and 21, and we start talking about reactions with carboxylic acids and their derivatives, it will start to make a lot more sense why they're considered derivatives of carboxylic acids. Because of that, section 19 has its own reactions. Sections 20 and 21 kind of have their own reactions. Aldehydes and ketones do not do the same reactions that all of the carboxylic acid derivatives do. We kind of create these two sets of carbonyls. Aldehydes and ketones, carboxylic acid, and the derivatives. All right, with our nomenclature, we could look at nomenclature of all acid halides. We're only going to be looking primarily at acid chlorides, so we're just going to keep that in the context there. We talked earlier in the semester that nomenclature kind of has several different parts to it. The prefix, usually the biggest part of the name. The root, the suffix, and I actually like to say that there's a suffix for the hydrocarbon and a suffix stopper for the functional group. So the suffix stopper for the acid chloride is oil chloride. I think somebody tried to tell me where they think that came from, but I don't remember. It stands alone. It's kind of unique, but it's a little funny looking. So let's look at an example molecule. Benzene with an acid chloride attached. This is benzoyl chloride. Instead of benzaldehyde, instead of benzoic acid, benzoyl. Although the legal name for acid anhydrides is acid anhydride, it's very common to just refer to them as anhydrides. So I want you guys to be comfortable with that. There's actually there's two types of acid anhydrides. There are symmetric and asymmetric acid anhydrides. So for the suffix stopper, oh, sorry. Yep, I got myself turned around there. The suffix stopper is oic anhydride. This is going to resemble our name for the acid. The suffix stopper for the carboxylic acid is oic acid. Here we get oic anhydride. And let's look at what happens when we have a symmetric molecule and an asymmetric molecule. Going to be introducing some other things about nomenclature as we go through these examples as well, so that you guys can see variations that come with it. I think I've talked about this 2-carbon carbonyl group a bit, and the 2-carbon carbonyl group is often given the ACET acid component. So this is acetic acid and acetic acid joined together, less a molecule of water. So this is acetic anhydride. Acetic is a common name. Acetic does not systematically tell you how many carbons are there. It's been adopted by IUPAC, but it's common. You'll notice that it's not acetoic anhydride. So I gave you the suffix stopper oic anhydride, but it's in common names, it's often removed. The systematic name for acetic anhydride. This is a 2-carbon chain on both sides. That's ethanoic anhydride. I love systematic naming, but not everywhere you look will have systematic naming. So when it's symmetric, when it's the same carbon group on either side, you just say what one of the carbon groups is, and then you say it's anhydride, so you know it's kind of a dimer on both sides. When it's asymmetric, you have to name both sides, and you just alphabetize them. So on the left-hand side, I would have had benzoic acid, and on the right-hand side, I would have had propanoic acid, propanoic being 3 carbons. So I have benzoic space propanoic anhydride. Pretty simple, right? Not that challenging. And of course, it can get so much more complicated. Let's say I want to put a benzene at the end of this 3-carbon chain. Okay, well, I'm not actually going to name it after the benzene. The longest carbon chain there, my parent chain, would be the 3-carbon chain with the carbonyls. So it would become 3-phenylpropanoic. And that would make it benzoic 3-phenylpropanoic anhydride. It just gets more cluttered, that's all. Okay, let's pick up tomorrow finishing the rest of our nomenclature. We're going to dive headfirst into reactions with aldehydes and ketones.